Now, since there were questions about the mean value theorem, I'm going to illustrate this first by making a comparison between the fundamental theorem of calculus and the mean value theorem. So we're going to compare this fundamental theorem of calculus with what we call the mean value theorem. And in order to do that, I'm going to introduce a couple of notations. I'll write delta f is f of b minus f of a. And another highly imaginative notation, delta x is equal to b minus a. So here's the change in f, there's the change in x. And then this fundamental theorem can be written, of course, right up above there is the formula, and it's the formula for delta f. So this is what we call the fundamental theorem of calculus. I'm going to divide by delta x now. And if I divide by delta x, that's the same thing as 1 over b minus a times the integral from a to b of f of x dx. All right, so I've just rewritten the formula here. And this expression here on the right-hand side is a fairly important one. This is the average of f. That's the average value of f. Now, so this is going to permit me to make the comparison between the mean value theorem, which we don't have stated yet here, and the fundamental theorem. And I'll do it in the form of inequalities. So right in the middle here, I'm going to put the fundamental theorem. It says that delta f in this notation is equal to, well, if I multiply by delta x again, I can write it as the average of f. So I'm going to write it as the average of f prime here times delta x. All right, so we have this factor here, which is the average of f prime, or the average of little f. It's the same thing. And then I multiplied through again. So I put the thing in the red box, right? Here. Isn't what the average of big F? So the question is, why is this the average of little f rather than the average of big F? So the average of a function is the typical value. If, for example, little f were a constant, okay, if little f were a constant, then this integral would be, so the question is, why is this the average? And I'll take a little second to explain that, but I think I'll explain it over here, because I'm going to erase it. So the idea of an average is the following. For example, imagine that A is equal to 0 and B is equal to n, let's say, for example. And so we might average sum the function from 1 to n, all right? Now, that would be the sum of the values from 1 to n. But the average is we divide by n here. All right? So this is the average. And this is a kind of Riemann sum representing the integral from 0 to n of f of x dx, where the increment, delta x, is 1. All right? So this is the notion of an average value here, but in the continuum setting as opposed to the discrete setting. Whereas what's on the left-hand side is the change in f, the capital F. And this is the average of the little f. Okay? So an average is a sum, and it's like an integral. All right, so in other words, what I have here is that the change in f is the average of its infinitesimal change times the amount of time elapsed, if you like. So this is the statement of the fundamental theorem. Just rewritten, exactly what I wrote there, but I multiplied back by delta x. Now, let me compare this with the mean value theorem. The mean value theorem also is an equation. The mean value theorem says that this is equal to f prime of c times delta x. Now, I pulled a fast one on you. I used capital F's here to make the analogy clear. But the role of the letter is important to make the transition to this comparison. We're talking about the function capital F here and its derivative. Now, this is true. So now I claim that this thing is fairly specific, whereas this, unfortunately, is a little bit vague. And the reason why it's vague is that c is just somewhere in the interval. So some c, sorry, this is some c in between a and b. So really, since we don't know where this thing is, we don't know which of the values it is, we can't say what it is. All we can do is say, well, for sure it's less than the largest value, say the maximum of f prime times delta x. And the only thing we can say for sure on the other end is that it's less than or equal it's greater than or equal to the minimum of f prime times delta x over that same interval. This is over a less than x less than b. All right? So that means that the fundamental theorem of calculus is a much more specific thing, and indeed it gives the same conclusion. It's much stronger than the mean value theorem. It's way better than the mean value theorem. In fact, as soon as we have integrals, we can abandon the mean value theorem. We don't want it. It's too simple-minded. And what we have is something much more sophisticated, which we can use, which is this. So it's obvious that if this is the average is less than the maximum. So it's obvious that it works just as well to draw this conclusion. And similarly over here with the minimum. Okay, the average is always bigger than the minimum and smaller than the maximum. All right, so this is the connection, if you like. And I'm going to elaborate just one step further by talking about the problem that you had on the exam. So there was an exam 2 problem. And I'll show you how it works using the mean value theorem and how it works using integrals. But I'm going to have to use this notation capital F. So capital F prime, as opposed to little f, which was what was the notation that was on your exam. So we had this situation here. These were the givens of the problem. And then the question was the mean value theorem says, or implies, if you like. It doesn't say it, but it implies it. Sorry. Implies A is less than capital F of 4 is less than B, for which A and B. So let's take a look at what it says. Well, the mean value theorem says that f of 4 minus f of 0 is equal to f prime of c times 4 minus 0. This is this f prime times delta x. This is the change in x. And that's the same thing as 1 over 1 plus c times 4. And so the range of values of this number here is from 1 over 1 plus 0 times 4, that's 4, to, that's the largest value, to the smallest that it gets, which is 1 over 1 plus 4 times 4. All right, that's the range. And so the conclusion is that f of 4 minus f of 0 is between, well, let's see, it's between 4 and 4/5, right, which are those two numbers down there. And if you remember that f of 0 is 1, this is the same as f of 4 is between 5 and 9/5. All right, so that's the way that you were supposed to solve the problem on the exam. On the other hand, let's compare to what you would do with the fundamental theorem of calculus.